The first second, what happened before everything existed. Welcome to Cosmic Depths. Today we are not going to the edge of the universe, we are going to the beginning of it. Not to a time billions of years ago, not to the formation of the first stars or the birth of the first galaxies. We are going further back than any telescope can see, further back than any fossil, any signal, any trace of anything that has ever existed. We are going to a moment so close to absolute zero on the timeline of reality that the word second is not precise enough to describe it. We are going to the first fraction of the first instant that anything was anything at all. And what we find there, what science has slowly, painstakingly reconstructed from particles and equations and the faintest echoes still traveling through space today, is not what you expect. It is stranger, more violent, more improbable, and more beautiful than anything the human imagination has ever invented. Before we go further, if this kind of journey moves you, hit the like button right now and tell me in the comments, do you believe something existed before the Big Bang? Or do you think existence itself started at that first instant? There is no wrong answer, but your answer will mean something different by the end of this video. Subscribe and turn on notifications because what comes next on this channel will go even deeper. Before time, here is the most disorienting fact in all of science. We do not know what existed before the Big Bang, because the question itself may not have a valid answer. Before that first instant, according to our best understanding of physics, there was no space, there was no matter, there was no energy in any form we recognize, and there was no time, not empty time, not dark time, not waiting time, no time at all. Stephen Hawking described it this way: asking what happened before the Big Bang is like asking what is south of the South Pole. The question assumes a direction that does not exist at the location you are asking about. Time, as we experience it, as we measure it, as we build our entire understanding of cause and effect around, did not exist before the universe began. That is not a poetic statement. It is a mathematical one, and it means that the Big Bang was not an explosion in space. It was an explosion of space. It was not something that happened somewhere. It was the creation of somewhere, of everywhere, of every dimension in which anything could ever happen at all. In 1927, a Belgian priest and physicist named Georges Lemaitre looked at Einstein's equations of general relativity and noticed something no one had fully confronted yet. If you run the expansion of the universe backwards, everything converges. Every galaxy, every star, every atom, all of it compresses and compresses and compresses, until you arrive at a single point of infinite density and infinite temperature that Lemaitre called the primordial atom, the cosmic egg, the moment before the first moment. He proposed that everything we see began there. Einstein initially resisted. The idea seemed too simple, too violent, too much like a creation story dressed in mathematics. But the evidence kept arriving. Edwin Hubble's observations of galaxies moving away from each other, the discovery of the cosmic microwave background radiation, the precise ratios of hydrogen and helium in the universe, until the theory that was once mocked became the foundation of modern cosmology. The Big Bang is not a theory about an explosion. It is a theory about the origin of space, time, matter, and the laws of physics themselves. And it begins with a fraction of a second so small that we do not have words for it in ordinary language. The Planck Era, 0 to 10 to the negative 43 seconds. The story starts at what physicists call the Planck time, 10 to the negative 43 seconds after the beginning. That number is not something the human mind can genuinely process. It is not a very short time in the way that a millisecond is a short time. It is a duration so incomprehensibly brief that all of human history, every civilization, every war, every empire, every life ever lived, compressed into that interval, would still be unimaginably larger than the Planck time itself. At this moment, the universe was not the size of a grain of sand. It was not the size of a bacterium. It was smaller than anything we have tools to measure. It was a point, or something like a point, where the temperature was so extreme, the density so absolute, that all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single superforce. Physics as we know it did not apply. The equations that describe our universe, that allow us to build computers, send signals across space, understand atoms, break down completely at this scale. The Planck Era is a wall. Everything before it is, for now, beyond the reach of human mathematics. What we know is only what came after. Inflation. The universe expands faster than light. At 10 to the negative 36 seconds, something happened that has no parallel in anything we have ever observed. The universe inflated, not expanded in the gentle, continuous way it still expands today. It inflated, violently, exponentially, at a rate that makes the speed of light look slow. In an interval of time so brief it cannot be written without scientific notation, the universe grew from a region smaller than a proton to something the size of a grapefruit. That may not sound dramatic. A grapefruit is not large, but understand what that growth rate means in relative terms. It is the equivalent of something the size of an atom expanding to become larger than the observable universe, in a fraction of a second. The expansion was not matter moving through space. It was space itself stretching, carrying everything within it outward simultaneously, at speeds that violated no law of physics because space is not subject to the universal speed limit. Only objects moving through space are. This period is called cosmic inflation, and the evidence for it is encoded in the structure of the universe we see today. The cosmic microwave background, the faint glow of radiation left over from the early universe, first detected in 1965 by Arno Penzias and Robert Wilson, shows an almost perfectly uniform temperature in all directions. That uniformity only makes sense if the early universe was once a single connected region that inflated faster than light. Otherwise, regions of the universe that have never been in contact with each other should have wildly different temperatures. They do not. The universe is eerily, precisely uniform, and inflation explains why. The quark soup, the universe's first substance. At 10 to the negative 12 seconds, the universe was still unrecognizably different from anything that exists today. But it had cooled enough, relative to its initial state, for something to begin. The first particles, not atoms, not protons, not even the components of protons. The universe at this stage was filled with a plasma of fundamental particles, quarks and gluons, moving freely through the superheated chaos, colliding and annihilating and reforming in a continuous violence of energy that we call the quark-gluon plasma. Its temperature was approximately 5.5 billion degrees Celsius, roughly equivalent to the core temperature of the largest stars that would eventually form billions of years later, compressed into every point of a universe far smaller than what we know. Scientists have actually recreated this state in laboratories. The Large Hadron Collider at CERN has produced quark-gluon plasma by colliding gold ions at nearly the speed of light, generating temperatures of several trillion degrees for a fraction of a second. For a moment, in a tunnel beneath the Swiss-French border, conditions resembling the early universe existed on Earth. What those experiments revealed surprised physicists. The quark-gluon plasma does not behave like a gas. It behaves like a perfect liquid, nearly frictionless, flowing with an efficiency that no substance at room temperature can match. The beginning of the universe was not a cloud of particles. It was a flowing ocean of fundamental matter, moving with impossible smoothness through impossible heat. The first second, matter wins. At approximately 1 microsecond after the Big Bang, something decisive happened. The quarks combined. As the universe continued expanding and cooling, the free quarks that had been flowing through the plasma began to bind together under the strong nuclear force. 3 quarks bonded to form a proton. 3 quarks bonded to form a neutron, the basic building blocks of atomic nuclei. The same protons and neutrons that exist in every atom of every object in the universe today, formed in the first microsecond of existence. But there was a problem. For every particle of matter that formed, a particle of antimatter formed alongside it. Matter and antimatter are mirror images, identical in mass, opposite in charge. And when they meet, they annihilate each other completely, converting entirely into energy. In the early universe, matter and antimatter were colliding and annihilating constantly, producing floods of radiation that immediately converted back into matter-antimatter pairs, which collided and annihilated again in an endless cycle of creation and destruction. If this process had been perfectly symmetric, if exactly equal amounts of matter and antimatter had been produced, everything would have annihilated. The universe would have become a sea of pure radiation, with no matter left. No atoms, no stars, no planets, no anything. But something went wrong, or something went right. For reasons that physics has not fully explained, slightly more matter formed than antimatter. The ratio was approximately 1,000,000,001 particles of matter for every 1,000,000,000 particles of antimatter. The antimatter annihilated with 1,000,000,000 matter particles. The radiation from those annihilations still fills the universe today as the cosmic microwave background. And the one remaining matter particle, the survivor, became everything. Every atom in your body is a survivor. Every star, every galaxy, every planet in the observable universe exists because of an asymmetry so small, 1 part in 1,000,000,000, that it could have gone the other way. It did not. And in that asymmetry, the universe chose to exist. 3 minutes. The first atoms begin. At 3 minutes and 46 seconds after the Big Bang, the universe had cooled to approximately 1 billion degrees. That is still unimaginably hot by any human standard. But it was cool enough for protons and neutrons to begin fusing together. The first nuclei formed, hydrogen nuclei, single protons, and helium nuclei, 2 protons and 2 neutrons, through a process called Big Bang nucleosynthesis. This lasted only about 17 minutes. After that, the universe had expanded and cooled enough that nuclear fusion could no longer occur. The ratio of elements was fixed, approximately 75% hydrogen and 25% helium, with trace amounts of lithium and beryllium. That ratio is not a historical curiosity, it is a prediction. Our models of Big Bang nucleosynthesis calculate exactly those proportions. And when we look at the oldest, most primitive stars in the universe, stars that formed before any supernova had enriched the cosmos with heavier elements, we find exactly those proportions. The first 3 minutes of the universe left a signature in the chemical composition of every star in the sky. We can read it, and what it says matches what the physics predicts. That is not a coincidence, it is confirmation. 380,000 years, the universe becomes transparent. For the first 380,000 years after the Big Bang, the universe was opaque, not dark in the way space appears dark today. Bright, intensely, uniformly bright. Every point in space was filled with a plasma of charged particles that constantly scattered photons, preventing light from traveling in any straight line. The universe was a fog of pure energy, so dense and so hot that no photon could travel more than a short distance before being absorbed and re-emitted. Nothing could be seen because there was nothing capable of seeing, and because seeing requires light to travel in a line, and light could not. Then, at 380,000 years, the temperature dropped to approximately 3,000 degrees. At that temperature, electrons slowed enough to be captured by atomic nuclei. The plasma that had filled the universe since its first moments suddenly transformed into neutral atoms, mostly hydrogen and helium. And for the first time, the universe became transparent. The photons that had been trapped in the plasma were released. They flooded outward in all directions, carrying an imprint of the universe as it was at that moment. The temperature, the density fluctuations, the seeds of everything that would eventually become structure. Those photons are still traveling today, stretched by 13.8 billion years of cosmic expansion until their wavelengths fell into the microwave range. They reach our detectors as a faint uniform glow from every direction in the sky. The cosmic microwave background. It is the oldest light in the universe's first photograph. And it contains, encoded in its faint temperature variations, the blueprint for every galaxy, every star cluster, and every planet that would eventually form. We can read that blueprint. We have been reading it for decades, with satellites designed for exactly that purpose. And what it tells us is that the universe in its earliest observable state was almost perfectly smooth, with tiny quantum fluctuations in density that gravity would spend the next billions of years amplifying into the cosmic web of structure we see today. The Dark Ages and the First Light. After the universe became transparent, it went dark. Not the darkness of plasma, the darkness of absence. There were no stars yet, there were no galaxies. There were no sources of light. The universe was filled with vast clouds of hydrogen and helium gas, slowly gravitating toward each other under the influence of dark matter, condensing over millions of years into the seeds of what would become structure. This period is called the Cosmic Dark Ages. It lasted from approximately 380,000 years after the Big Bang to somewhere between 150 and 500 million years, when the first stars ignited. Those first stars were nothing like the stars we see today. They were enormous. Some estimates suggest hundreds or even thousands of times the mass of our Sun. And they burned at temperatures so extreme that they blazed with ultraviolet radiation intense enough to ionize the hydrogen gas around them. They lived fast and died violently, exploding as supernovae and seeding the universe with the first heavy elements: carbon, oxygen, nitrogen, iron, the elements that would eventually make planets, that would eventually make life. Every atom of carbon in your body was forged in the heart of a star that lived and died billions of years before the Sun was born. You are not separate from the universe's history. You are made of it. What the first second means. Here is what is extraordinary about all of this: the entire structure of the universe. Every galaxy, every cluster, every filament of the cosmic web was determined in the first fraction of a second. The density fluctuations that inflation produced, so small they were quantum in origin, became the seeds of structure that gravity spent billions of years amplifying. The asymmetry between matter and antimatter, 1 part in 1 billion, determined that anything would exist at all. The ratio of fundamental forces, calibrated to a precision we do not fully understand, determined that atoms could form, that stars could ignite, that planets could orbit, that life could emerge. Change any of these by a small amount. Make the asymmetry slightly smaller, change the ratio of forces by a fraction, and the universe we know does not exist. It produces a cosmos that is all radiation, or one that collapses before stars can form, or one that expands too fast for gravity to build anything at all. The universe we have is extraordinarily specific. The first second produced conditions tuned, with a precision that still challenges our understanding, to allow everything that followed. We do not know if that precision is a coincidence. We do not know if it is one of many universes, each with different parameters, and we simply find ourselves in the one where the parameters permitted observers to exist. We do not know if there is something deeper, some principle of physics we have not discovered, that makes these values not arbitrary but inevitable. What we know is that it happened, that the first second produced a universe that 13.8 billion years later contains minds capable of reconstructing what that first second was like, that the physics written into the first instant of existence eventually produced creatures who could read that physics and understand their own origin. That is not a small thing. That is perhaps the most remarkable fact in the history of anything. The echo we can still hear. Right now, at this moment, the echo of the first second is reaching you. The cosmic microwave background radiation, the photons released 380,000 years after the Big Bang, is arriving at every surface on Earth, passing through your body, filling the space around you with the oldest signal in the universe. If you could tune an old analog television to receive it, a fraction of the static on the screen would be photons from the beginning of time. The universe is not a distant thing we study through telescopes. It is here, around us, passing through us, carrying the record of its own creation in every direction at every moment. The first second of the universe did not happen 13.8 billion years ago in some location far away. It happened everywhere. It was the creation of everywhere, and its echoes have been expanding outward ever since, carrying their ancient message to every point in the cosmos, including this one, including here, including now. The universe began once, in an instant so brief it has no name in ordinary language, and in the 13.8 billion years since that instant, it produced space, time, matter, energy, stars, planets, chemistry, biology, consciousness, curiosity, and a species capable of looking back at its own beginning and asking what it means. We do not have a complete answer, but the question itself, the fact that the question exists, is the universe understanding itself. And that may be the whole point. If this journey to the beginning of time moved something in you, subscribe to Cosmic Depths and stay with us. The universe is still expanding, and we are just getting started.